Blah, 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 blah. Yes. Okay, we should start the lecture. And good. So today is the third lecture of the Advanced Cognitive Modeling course. And what we've done so far is that in the first lecture, we've discussed the conceptual framework of cognitive modeling. And we have formalized throughout the first and second class and the last lecture models of agents playing the matching pennies. Right? That is, we try to formulate the mechanisms that might generate the behavior observable throughout the task, where the mechanisms are not directly observable, but they can be reconstructed through introspection, literature from cognitive science, work, blah, blah, blah. And by formalizing the mechanisms that generate the data, we have been forced to think more precisely about what we mean with different pieces of our models. If we say that memory is constrained, how do we implement a memory constraint? Right. And we have then simulated behaviors generated by our models, because the models that we build are not always obvious. And I'll get back to that. The implications of the models are not always obvious, but also because, as we will see in the second part of today, once we create simulations from the models, we have data where we know the ground truth. We know which model has generated them. We know what are the parameter values that have generated the data, which means that when we build our inferential models that try to reconstruct either which out of n models is generating this data, or what are the parameter values of the model that has generated this data, let's say in reinforcement learning, what's the learning rate, we can see whether the models are actually any good at reconstructing these parameters. Good. So what we're going to do now is, if you have any outstanding questions, please ask them or put them in the Google Doc. Any questions that you have about what we've been doing so far? Nope. Good. Well, bad. I don't know. You know that? So the next thing is, I've had a chance to look at the first 4 submissions of the first assignment. And it's actually, of course, there's a very strong selection bias, meaning I've only been able to check those assignments of the groups who felt confident enough to submit in advance of the deadline. But so far, I have a very good impression. It feels like we can go a bit faster than in previous years, but we'll see. There's very good programming skills, both in R and in Python. There's, in most of the assignments that I've seen, very good reflections on the limitations of the models in the light of the cognitive literature. Not in all of them, but on the other hand, it wasn't a requirement, right? This is a programming kind of exercise, but I was pleasantly surprised by the general reflections and use of literature. What I think we could do slightly better, not because, again, it was required or showcased so far, but because it's something that we're going to build together, is we could do a better systematic exploration of parameter values. Let's say if you have a probabilistic Wins-Taylor shift, right? What are the implications of varying systematically the probability of staying when you win. And visualizing that. This is both at the level of simulation and visualization, but also more conceptually. As we build these models, we should always reflect explicitly on which landscape is the model assuming. That is, if we have a Winds-Taylor shift, right, it's a model that, if we assume it to be a good model, requires a specific kind of opponents to win. If we play, as I'll showcase in a few slides, so I'm not going to spend too many words right now. If we play reinforcement learning with a low learning rate, what are the conditions under which this would be a good model, right? A good strategy to solve the task. And that's something that I'm going to insist throughout the course, because it's something that we rarely, or we don't see it in most of the literature, because we're always very keen in pushing our models as the best solution. But all the models, like there is no free lunch, all the models are crap in most contexts and decent in some. And we need to sort of figure out, be very aware of what are these regions in which it's gonna work. Also because these ideas have important consequences. So what we're gonna do today is we're going to do a little bit of consolidation that is repetitions of what we've been doing last week, just focused on reinforcement learning, right? How do we build an agent that is a reinforcement learning agent? How do we systematically test and visualize the different implications of the model? How do we think when this is a good model and when it's a bad model? And then we're going to be moving from data generating to data inferred models. That is, we'll start with Stan. And the reading for this week will give you much deeper details on what we do when we program in Stan that we can cover this week and the next. So it's a nice complement to the lectures. Good. So reinforcement learning. So reinforcement learning was, let's say, formalized in a complete shape for the first time in a paper, a theory of Pavlovian conditioning, variations in the effectiveness of reinforcement and non-reinforcement by Robert Rescorla and Alan Wagner. And it's one of the examples in which we say that research in psychology has shaped neuroscience and computer science. And it's been sort of established as one of the dominant models in the field of cognitive modeling, but also in computational psychiatry, for instance, and also in a whole literature on deep learning. And lots of that is covered in the handbook by, I think it's Richard Sutton, yes. Which is a really, really cool handbook and free online. But the key aspect of reinforcement learning that makes it one of the best examples of cognitive modeling is that it's a model that is inspired by our reflections on how learning works from a cognitive perspective, right, in terms of information flows. And then it has been shown to reflect very well the way in which neural activity in terms of dopamine receptors in rats actually functions. So we've discussed it briefly. I have a few slides on that later, but the basic idea is that the way that we update our expectations on the word is not in terms of the raw feedback that we get from the word, but in terms of the difference between what we expect and the feedback that we get from the word. If we expected a reward and we get a reward, there is no reason to change our expectation. And indeed, there's several very cool experiments on rats where they can show that the neurons related to the dopamine receptors are only firing when there is a reward that is not expected. but not if there is a reward and it's expected. And it's a perfect example because it's a mechanism that can be applied to lots of different domains. If you look at the literature in computational psychiatry, basically a third of the papers are, what if we use reinforcement learning? Another third is, what if we did more reinforcement learning to explain whatever, right? Everything in the symptomatology of condition X can be explained by a slight twist in the learning rate from negative feedback in this specific domain, and that will cascade into depression or into general anxiety. And now I'm making fun of that. It's a grand dream that we can have simple cognitive level mechanisms that explain a broad variety of psychiatric symptoms, which generative mechanisms we still don't understand. It would be fantastic, right? We know that it never works, right? It can explain a tiny little bit, but it is a step, right? It's also a really great model because it allows to triangulate between theory, behavior, and neural activity, right? A lot of the, I can't remember what it was called, but it was this big model by DeepMind that was able to play Atari games that made a very big splash, that a science paper. Can't remember the name. That was basically a reinforcement learning based machine. A lot of the AlphaGo and AlphaZeros are models that have lots of components, but one of them is a reinforcement learning activity. Right. Okay, how does the reinforcement learning works? Right. This is a schematic representation, but basically it has an agent, for instance, a human participant or a computer algorithm that is trying to learn how to play Go, that interacts with an uncertain external word, for instance, experimental setting or a game of Go. And it uses the feedback from the environment, for instance, rewards or punishments, to form internal values for the actions or decisions that it can take. Right. So in the matching pennies, it's kind of almost trivial, right? It's left or right. That's the two possible decisions. In an Atari game where you have a two-dimensional space, right, with hit and jump, right, you can have a combination of the possible directions and actions that you can take. And the agent needs to learn how to associate an expected value to an action or a sequence of actions. Right? And the way it does that is it has this set of feasible action. It looks at what is the expected value of each of these actions, right? If the model is complex, given the context or given the sequence in which they are set up. It chooses one of these actions and it acts out in the world. The action in the simple versions of the models gets a reward. In the more complex versions of the model, eventually gets a reward. This reward is compared to the expected value of the choice. The predictive error is used to change the representation of the expected values of the actions. Right? That's the basic idea. And so, yeah, I've done that. And it's called reinforcement learning because learning is the key mechanism. We update the expected value according to what we meet in the word as a response to our actions. And it's reinforced because positive, that is above expectation, feedback strengthens the expectation, increases it, and negative below expectation weakens the expectation. So there's two key parameters, one that we discussed slightly and the other that is not new, but we haven't discussed it explicitly. The learning rate, that is a parameter usually called alpha, that moderates the impact of predictive error on the change in expected values, right? So if we have a high learning rate, predictive errors strongly update our expectations. It means we learn faster. It also means that the past doesn't matter as much. It's always a trade-off, right? How much weight are you putting on the past? How much weight are you putting on the current trial? The higher the learning rate, the higher the weight on the current trial, the lower on the past, and vice versa. So actually, little fun exercise. When would a higher learning rate be an optimal value, a good value for a reinforcement learning algorithm? What does a high learning rate assume about the world? Yes.
That the world changes a lot.
Yes. Good. So if the world changes a lot, right, then we need to sort of be always following it, and memory shouldn't drag us down. What about a low learning rate? I know, Malte, you had your raised hand.
I was going to say the same thing.
Yeah.
A low learning rate is good, I guess, if there's a lot of noise, but
Yes.
the underlying rule doesn't change too much. You don't want to learn from all the noise.
Yeah, actually, it's probably orthogonal, right?
Yeah.
You have how much is the underlying rate changing and how high is the noise, because you could decouple that in the generative mechanism, right? Yes, but you're right. So if it's very noisy and it changes very fast, good luck. So good. This is one of the assumptions that the model has, right? A different kind of learning rate assumes a different kind of landscape. But what if you have weird planet where things like seasons change, right? Where you have some relatively fast change at certain periods, and then things do not change. Well, the temperature and stuff changes in a more continuous way, but the way that the environment produces nutrients and resources has a different tempo, right? Which kind of model would be good? Yes, Malte?
Maybe I'm jumping the gun, but you could have like a hierarchical learning rate where there's different learning rate that updates your learning rate.
Yes, right. So the idea is the Rescorla-Wagner reinforcement learning model assumes that there is one fixed learning rate, which is a good strategy, which assumes that the rate of changes in the environment is not variable. Right. There are models, and for instance, one of my colleagues and your teachers, Chris Mattis, has developed one that tries to deal with that sort of things by not just learning or having a learning rate, but having hierarchical parameters that try to estimate how fast the environment is changing and therefore adjusting the learning rate, and how you can go many levels of recursion. So how it's not how fast, but well, how fast is the speed of changing, right? And blah, and blah, and blah. Also, how noisy is the data, and accordingly adjust the learning rate. The other parameter, here is the stuff that I had promised. Yes, I'm just gonna move these away if I can. Yes. Okay. One of the things that I mentioned a couple of times, and I wanted to make good on my promise, is to show you why a learning rate, as it is implemented in reinforcement learning, implies an exponential decay of memory. Right. So here we have that the value at time t is given by, well, this is a slight reformulation. So if you remember, we had the value at time t minus 1 plus alpha times the predictive error, which can be re-parameterized as if we move the predictive error out of the reward, it can be reparameterized as 1 minus alpha times the previous expected values plus alpha times the reward in the previous trials. which can be sort of unpacked because the expected value of t minus 1 is something that we calculated with the same formula. So we can sort of unpack it here. And then what we can do is we can do that recursively until we get to the beginning of the trials. And these unpacks as 1 minus alpha to the power of t minus 1 times the first expected value plus the sum from 1 to the current time of 1 minus alpha to the power of t minus I minus 1 times learning rate times the vector of rewards. Right, so the basic idea here is that these previous expected value is something that we can unpack throughout all the previous trials. And as we do that, we have that the alpha is 1 minus alpha in this case is changing what we learn, the impact of the reward at time I or t in a decreasing way the further you go. Right, so t is the higher, the closer you are to the current trial, which means that alpha is going to impact the effect of the reward in a higher way the closer it is to our current trial. Good. Yes.
It's just the wording when you say you can unpack
Yeah.
the previous expected.
Yes.
Do you mean it's something you can estimate or?
Oh no,
Or do
so
you
this is actually simply analytically derived. Is
So
there?
it's like unpack is analytically.
Yeah, so the idea is that you take these equation and then you can take v at t minus 1 and actually sort of take these equation and replace that.
Yeah, okay.
And then inside that, you're going to have t minus 2, and you can take that and
Further,
use these equations to put that inside.
like a babushka doll.
Yes, exactly.
It makes sense.
Yeah.
I got it.
Yes, and this corresponds to the intuition that we discussed before, that if you have a weight of 0.1, in the previous trial, it means that the previous trial counts 10% and the current trial 90%. But the previous trial has to be opened up as a babushka doll, which means that of that 10%, 90% is the t minus 1 and 10% is t minus 2.
Yeah.
But also that t minus 2 can be opened up, right?
Yes.
And that means that we go to 10%, 1%, 0.1%, right? And these is an exponential decay of how much it matters for the learning. Yes. Good. And one of the things that we do once we have a learning rate, right, is we always need to sort of try to visualize how things work. So here we can use these equations to simply simulate, given a learning rate of 0.9, how much does the current trial count? How much does t minus 1 count? How much does t minus 2 count? We can see that with a high learning rate, the recent trials count for a lot and they decay really fast. Right? The memory is lost very, very quickly. As the learning rate decreases, the importance of the current trial becomes less prominent, but it decays lower. Temperature is the second parameter of a reinforcement learning algorithm that says that given the expected values of the possible choices, how much determined are we by the one that is the higher, that has the higher expected value, right? It's what often is called exploration exploitation trade-off, right? If we want to exploit, right? If we trust what we learned so far and we don't feel we need to explore our option further, as soon as there is one choice that is even slightly higher in expected value than the others, we should just go for that. That would be a low temperature, or given that people developing these models like to mess with us, high inverse temperature, and high exploitation. If instead we feel like that there is noise in the environment, that we still want to explore the options and so on and so forth, we can have a low temperature or low inverse temperature or high temperature, yes, low inverse temperature or high temperature, which says that we still, if there is, let's say, 0.51% of the expected value is in choice A and 0.49% of the expected value is in the second choice, we still should try the second choice a high amount of times. Now, in the reinforcement learning literature, at least for the basic models, just like there is a fixed learning rate, we also tend to have a fixed inverse temperature. There is a fixed trade-off between exploration and exploitation. In more fancy models, you have different ways of setting that up. For instance, you might have a low inverse temperature that is a high exploration in the early phases of the learning, and a high inverse temperature. I hate that they talk about inverse temperature. That is a high exploitation in the later part of the model, which is a procedure that is called annealing, and that is observed in a lot of physical systems like glass. There was a question there.
Yeah, can you make a parameter for inverse heat or temperature?
Yes, we're gonna.
That has nothing to do with softmax choices.
So I
I'm
think
just
that,
curious, can it live outside of that? If we can make a mechanism that's not softmax.
so I think that, so the concept of temperature is independent of the softmax, but I've mostly seen it implemented as in the softmax. You can have, so if you know about the sigmoid growth curves, basically what you have an equation that describes the sigmoid, and there is a term for the ceiling and a term for the pavement. If you keep those towards the center, that corresponds to high temperature. So it's a different implementation. It's basically a softmax where you can have asymmetric pavement and ceilings. So it's still within the framework of the softmax, but in principle, there are other ways. I haven't looked in depth into other ways of doing that. Okay, so we simulate the data. I create a function which has as an input the expected value. It's not remembering things. I need to keep an external memory of the expected value on a trial by trial base. It has an alpha, that's the learning rate. It has a choice in the previous trial, and it has a feedback in the previous trial. I calculate the predictive error, feedback minus value. And then what I do here is something slightly different from what I said last week. That is, I take the value for the first choice, and I say that it's equal to the value for the first choice at the previous trial. times alpha, 1 minus choice, times the predictive error. And I take the value for the second choice. And I say that it should be updated according to the reinforcement learning rate, the choice, and the feedback minus the value for 2. Yes?
Two questions, I guess. One is, are these not just complementary?
In our case, yes.
In our case, it is.
Yes.
Okay, sure. But you have reasons to make like this for.
In the matching panels, they are complementary, and that's why I'm.
But I really wanted to ask is that we did reinforcement learning last semester.
Yes.
And there we discussed it a little bit, but the default way from history seemed to be that you only update the case that you experienced this trial.
Yes.
So for our gambling test, the other 3 decks you wouldn't touch. They would only be kind of implicitly change the value by the softmax balance kind of changing a little bit.
Yeah.
But you only touch the one. Do you have reasons to?
So this the difference between what we call the Riscorno-Wagner model of reinforcement learning and the counterfactual model of reinforcement learning, where the counterfactual model of reinforcement learning explicitly updates the value of every possible choice. Meaning that in this case, it's pretty trivial, right? Because if we know the reward for playing right, we also know what would have happened if we played left. But in other cases, it might not be, right? So if you're playing an Atari game, the value of jumping and firing might be quite independent from the value of turning left. Right? But if the jumping and firing brings us eventually to a reward, we downplay the potential, the expected value of the other choices as well. Explicitly, compared to just given the sigmoid. There's something wet here. For the people of the Zoom, there was something wet on the table and I put my hand on that and I have no idea what it is. Okay, so then we create a vector with the 2 updated values and we return it out. And then we have the softmax equation, right? That takes an x, that is the expected values, the tau, that is our inverse temperature, and then it basically has the sigmoid function, right? 1 divided 1 plus the exponential of minus tau times the expected values. That means that if we have an algorithm that for not to have to simulate too many times, we just say that it always chooses 1. And we make it play against an algorithm that is playing, how is it? 1, 0, 1. Well, it plays, I think, 90% of the times 1, and it has a fixed sequence. We can see what the feedback is. That's the red, right? We can see that when the other is playing 1, we get a feedback of 1. When the other is playing 0, we get a feedback of -1. Then the other keeps on playing 1, and since our algorithm just plays 1, it gets 1, 1, 1, 1 of feedback. Then it plays 0 again, and gets -1, and so on and so forth. And now we see what happens to the expected value with a learning rate of 0.9. Starts playing 1, and the expected value of playing 1 goes very quickly to 1. As soon as the other plays 0 and the algorithm gets a negative reward, then immediately the expected value of playing 1 goes down because we have a very high learning rate. We get a second 0. which means that it really goes almost to like full, we should always play 0. Okay. But then as the other plays 1 again, right, our expected value goes up there. And then it goes down again the one time that we get a 0 from the other, and then it goes up again. Right? This is where we were saying that a high learning rate is potentially suboptimal when there is a noisy signal. We're getting every now and then these zeros, and the algorithm immediately jumps to conclusion. The other side of the medal is that, of course, given that the noise is very limited in this example, our algorithm really goes back very quickly to the right expected value, right? And as we vary the reinforcement or the learning rate from 0.9, the purple, to 0.5, the blue, to 0.2, the green, we can see how the occasional spike of zeros is impacting the algorithm less and less, which is a good way to understand how the learning rate works. Good. Now we can see how it performs against an algorithm, a random bias that plays 75% of the time. Yes?
I think I missed it, but the tau in this plot
Is not.
is not included.
No, I'm just doing it step by step. Yes. Here we include tau. Yes. Now we just want to explore the full range of values, right? All the learning rates from almost 0 to well, I think I put it from 0.1 to 1, and a bunch of different values of tau, from very low inverse temperature that is very high exploration to very high inverse temperature that is very high exploitation. And we can see that here are the alphas, right? We can see that the some algorithms in a regime of high, low inverse temperature, that is high temperature, they're really mixed, right? It goes all over the place because it keeps picking almost at random, right? If we go to a very high inverse temperature that is very low exploration, we get, and instead they're organized in a much more linear way, where low learning rates are actually better performing because they don't get swayed by these occasional spikes of ones. And here is exactly the same kind of plot, but instead of representing with colors the different learning rates, I represent the different taus with colors, and the different panels represent the different learning rates, because sometimes that gives us different insights. Right. This is just an example of how it's actually quite important, and I haven't done it enough in this example, quite important to systematically explore the space of the parameters and which impact they have. Because we can see that, for instance, given how much temperature we put, the learning rate will have a different impact, right? Will make a different difference. Yes.
So this temperature parameter, that's related to how you translate the expected utility to an actual decision.
Yes.
Okay.
And
so,
actually, yeah.
And so in this case, if my intuition is correct, so yeah, first I saw a high value here would mean a steeper decision boundary.
Yes, that's a high inverse temperature, which is a low temperature. Yes. Yes.
So my intuition, and there's no shift in the bias. It's always at 0 or 0.5 or what you call it.
Yeah, so here it's yeah, there is no bias given the so the decision is entirely determined by the expected values and the temperature. There is no
Am I
third
correct?
parameter.
My intuition here is that the higher value of tau would always be better in the long term here, because there is no reason, as long as I'm you know, 51% sure that you pick something, I can just as well go with that and
Yeah.
return the open the better decision.
Yeah, exactly. It might not be a good strategy if you have a changing environment.
Oh,
Yeah. And so here I haven't put that plot. Blame the winter holidays. I'm not the master of my time. But there should be a plot that draws the sigmoid with different inverse temperatures, where you would exactly see that the sigmoid becomes steeper and steeper the higher the inverse temperature it is. That is, the decision boundary becomes more and more deterministic the higher the inverse temperature it is. And more probabilistic the lower the inverse temperature it is. Okay. Let me see how we're doing with time. Okay. I have just a few quick slides here before we enter Stan after the break. So the models that we dealt so far with are random bias, right? Where there is one parameter, that's rate. Rate goes from 0 to 1. And the form of the model is simply that the choice is sampled from a binomial distribution, trial by trial, with a rate determined by the parameter value. We've seen the noisy random bias, which is exactly as before, except that we sample also from a distribution, a binomial distribution of noise. And if we get that we're lucky and this is a noise trial, the choice is sampled from a binomial distribution with a rate of 0.5. So it's completely random. We've seen the probabilistic win-stay-lose shift, where the parameters might be the probability of staying when you win and the probability of living when you lose. And I just wanted to take a few minutes to see how would you express this in terms of a model. And I really want, I'll go and fetch some colors in the break. But so because you can express that model with a if structure, which is the most intuitive way of doing that, but you could also express that very model as an instance of the generalized linear model. And it's a good exercise to be able to move between these different ways of formulating the models, because in some cases, one form will be more convenient, in other cases, the other will be more convenient. How would you formalize a probabilistic win-stay-lose shift in terms of a generalized linear model, in terms of an equation that is like y as determined by 1 plus x, 1 plus x2 blah. Yes?
I guess you need some sort of, I don't know if you call it a parameter, but something that takes into consideration the like symmetry of if you choose left, then that's correct, or if you choose right and that's incorrect, then your choice should be more towards left and reversely.
Yes.
Right, or something.
Okay, basically you want to create a derived variable, right, which we're not estimating, but it can be deterministically calculated from
Yeah.
the current trial, right? That is giving us where the direction should be if stay is relevant, and nothing if stay is not relevant, and a variable that tells us what the direction should be if leave is relevant, and nothing if leave is not relevant. So, any suggestions on how we would do that? All right, we can say if, oh yeah, sorry.
Yeah, no, it's just like you need some sort of auxiliary variable, which is determining whether you're gonna stay or leave. I'm not sure about the notation, I think, but you need to put that in there. and
Yes,
then-
so you need to create new variables, right,
Yeah.
that we can feed to the model. And so it would be if the reward, yes,
Maybe I'm missing the question, but if you define a variable called feedback,
mm-hmm,
and it could either take 0 or 1. 0 means you lost,
yeah,
and the choice 1 means you won.
yes,
Then you can make like a linear equation with saying stay p times feedback plus leave p times feedback. Right, because then if the feedback is 0, if you lost, then you only keep.
If it's
The-
0, you lose both, right?
You're right. So is it time, the other variables would be one out of feedback, does that make sense?
Yes, exactly.
I'm not sure the person, so do we have, are we assuming we have the decision, or do we need to derive an equation like?
So
the
we
binary
have
of
the-
Decision.
We have the decision at the previous trial, and we have the reward at the previous
okay,
trial,
you're
and we
asking-
need to define the current choice.
Okay, so first you need to translate the binary win or lose variable, plus, so you have the win or lose, and you
Mhm.
have the left or right.
Yes,
And you can derive a very simple equation which translates that into a third binary variable, which is stay or leave.
yeah, except the choice is not in terms of stay or leave, but it's in term of left or
Left
right.
yes.
Yes.
it's left or right on the next.
Yeah.
Yes. So that you will need, and then you need to use that variable as a switch between the two probabilities
Yes,
that you have as your parameter.
Yeah. exactly. So let's assume that we have a symmetric probabilistic model. That is, the probability of staying if we win is the same as the probability of living if we lose. Right?
we can have a variable that says, if we won and we played left, -1. If we won and we played right, 1. If we lost and we played left, we inverted, right? So 1. If we lost and we played right, we inverted, so -1. And then we have that the model is a binomial or logistic regression, where y, the rate of choosing right, is determined by an intercept that could express a bias, whether we tend generally to play more left or right, plus beta times this new variable that we created. So if that variable embodies the rule of win, stay, lose, shift, and the beta embodies the probabilistic part of the model. Does it make sense? If we want to make it asymmetric, right, we need to create, instead of one variable, 2 variables that have 1 and -1. So the first one, the win variable, has -1 when we won and we played left, +1 when we won and we played right, 0 if we lost. The other variable, the leave variable, has 0 if we won, no matter what we played, because it's not relevant. The rule doesn't apply, so we want to rule it out of the equation. And it has +1 if we lost and played left, -1 if we lost and played right. And then our equation would be a logistic, where the rate is determined by our intercept plus stay p times this stay new variable plus leave p times this leave new variable. And sometimes we need to get creative to turn these more complex rule into something that's easy to solve, right? And we'll take a break and then I'll write it on the whiteboard so it's easier. Good. Okay, we should start again. So, oops. Basically, we were here, right? So what we do is we create a new variable for the symmetric Winds-Taylor shift, which follows the rule, right? It's the Winds-Taylor shift rule translated into which choice we should make. So if we win the first two, choice is right, we give 1 because that's what the model think is right. And if the choice was left, then we choose -1 because that goes against choosing right. If we lost, then we do the opposite of the rule. And then we simply specify the model as 1 plus this new variable, right? Which of course, it would have a beta, which is the probabilistic, the amount to which the participant would actually follow that rule. If we have the asymmetric Winds-Taylor shift, right, we have in the blue the case in which we win. If the choice is right, a state variable is 1, more right, and a leave variable is 0. It's not relevant. If the choice is left, the state variable is -1, and the leave variable is 0. If instead we lost and the choice was right, the state variable is 0 because it's not relevant. The leave variable is -1, the opposite, right? We should choose left next time. We should leave right. And if the choice was left, it's the opposite. And the traditional generalized linear model would be that y is given by 1 plus state variable plus leave variable, which automatically brings in the two parameters, beta stay and beta leave. Right? Does this make a bit of sense? Yes, Mark.
And then there's a logistic transformation.
Yes. And then, well, if we were running this in LME4 or in DRMS, we could simply specify that the family is a binomial, right? Or a Bernoulli if we want to be fancy in DRMS. Meaning that what we have here is a linear model, which could assume, and I forgot again actually, let's take the simple one, right? For simplicity. We have that Winds-Taylor shift, our new variable could be 1. And our beta, let's say it's a probabilistic model that's very close to deterministic, could be 3. Right? What we would have is that our intercept could be 0. There's no bias, right? So we would have that our y is 0 plus times 3 times 1, which means that y is equal 3, which should push us towards choosing right most of the time, almost every time. But it's a 3, right? How do we go from a 3 to a binary choice? Do you remember your logistic regressions? Right, so basically, what we say is oh, yes, here we are in the magical space of the linear model, where every value is legitimate. It can go from -infinite, which is very close, well, it's always 0, to +infinite, which is always 1. And we need to sort of shrink it to the 0 to 1 space. And the transformation that does that is transforming it from log odds, so assuming that this linear space is log odds, and transforming it back into probability, right? Which is log of p divided 1 minus p. This is the log odds, right? And you can say that 3 is equal log of p divided 1 minus p, and we can solve it. I'm not going to do that on that because I use the computer to do that sort of things. But what happens is that here we have a space that goes from, on the x-axis, sorry, people of the Zoom. On the x-axis, we have a space that goes from 0 to, so from minus infinite to plus infinite. On the y-axis, we have a space that can only go from 0 to 1. And if we follow that equation, what we have is that there is basically our beloved sigma function, where values that are close to 0, we can transform in something that's close to 0.5. Values that are positive are more than 50% chances of picking 1. The further we go into the plus infinite space, the more certain we are that we're going to pick 1. And if we go below 0, we get more and more likely to pick 0 is left. Right? So basically, saying if you're using the BRMS function, inv logit scaled of 3, right, gives you a probability that's going to be 3. It's probably 0.9 something, 7, I think, something like that. If you're using the boot function, it's simply inv.logit, whatever, it does the same thing. And so basically what we have here is the ability to work in a linear model, which we know, and we can put all sort of predictors in and transform it back to a rate, which we can give then to the binomial distribution and pick a binary choice. Thanks, Malte. I hadn't put it in the slides because I thought you went through that many, many times, but this is the sort of things that actually we should always go through because it's the hard part, right?
We discussed it a little bit with the last semester, but he said, let's just do it this way for now. And then I don't think we returned to it. I don't remember.
Okay, but there should be in method 3 and methods 4 at least, right? Yes, but fair enough. And then I did it again. Sticky fingers. Yes. Okay, good. That's the 3 of the models that we have. Then we have the reinforcement learning model, which is very different from the models that we discussed, because the reinforcement learning model cannot be reduced to a generalized linear model. Why? This is something we haven't covered, so you're not expected to know. But this is one of the cases where we need to go to stat. We cannot use BRMS. Yes, Malte?
It's recursive, or like each value depends on the previous trial.
So in the generalized linear model, if you remember your methods too, right, we rely on all these fancy matrices, which means that we want to have all of the predictor variables present at the same time, which means that we can calculate the most likely given the maximum likelihood, or the most likely given the likelihood and the prior if we're in Bayes, beta values that connect those predictor values to the outcome variables, outcome values. But in the reinforcement learning, we cannot have all the values that we need to calculate the parameters at once, because the value of the parameter, let's say the learning rate, will affect on a trial by trial base the expected value, which means we cannot have all the expected values as a given in the methods, which means that we need to calculate all the possible behavioral sequences given these specific reinforcement learning rate and their log posterior probability. We'll get there, what that is, but their likelihood given the data. And we need to do that on a trial by trial basis. Okay, and these has two parameters, the learning rate and the inverse temperature, alpha and tau. So what we're going to do is that now we have a set of plausible and interesting cognitive models. I haven't listed all the ones you have in your assignments, not because they're not plausible and interesting, just because I had to limit the space on the slide. And we need to check them against data, right? We need to figure out, given these models that we've been so clever in devising, right? Do they have internal validity? For instance, if we generate data that follow that model, can we fit the very same model to those data? Right? Does it even work? It should. It doesn't always work because we're not as clever in designing models. Usually it's our fault. Or, you might be loading shuffled data, but then the model doesn't work. If there are parameters, let's say bias, let's say the probabilistic parameter in the Wien-Staley shift, let's say learning rate and tau, inverse temperature. Once we generate the data according to systematically all the combination of these parameters, is our model able to infer them back with the right value? Is it going to give us the right value? If we have more than one model, and later on we will do that, not this lecture nor the next, but we generate data from reinforcement learning and we generate data from random bias, can we use model comparison techniques to reconstruct the true model that has generated the variable? It's not going to tell us if these models are going to be any good out in the world, because out in the world, we don't know the models that generated these data, but they tell us if in this very Hygge environment where we know the truth, do they even make sense here? Right? That's why I call it internal validity. And then what we will need to do is we will need to consider external validity, right? We know that the models in principle can function. We need to go and take empirical data and then say, well, if we fit the data to the models to these data, are the models able to capture the patterns in the data, right? And if the model is crap in terms of external validity, it's a beautifully elegant model that was very cleverly devised, and you swore for 2 months to make it fit the data that you generated from the very same model. But if participants are using a completely different mechanism, it might be very crap at describing those patterns. And that's actually a good thing, because that tells you that's not the good model, and we learn something. And also, if we take different models, how do these models compare in their predictions to the empirical data? We might have that different participants are following different models. We might have that those accursed participants are shifting strategy throughout. It might be that in certain conditions, they tend to be more similar to model 1. In other conditions, they tend to be more similar to model 2, right? When we have the participant play with algorithms that have a high level of recursion in their theory of mind, they might revert to something that's closer to random behavior because they just can't figure out what's going on. Right? And so these are the kind of things that we need to learn how to do in order to figure out what can we use our models for. So the way that we do that is we specify the model in a model fitting environment that is in STAN in the case of this course, in terms of a likelihood and parameters that are connected to each other with mathematical functions. And in terms of priors, that is, given that we're doing Bayesian cognitive modeling, we want to pre-establish what are likely ranges of values for these parameters. We'll do a lot of that. We want to assess the model predictions before seeing the data. This is what we call the prior predictive checks. That is, we say, given the priors, the likely regions of parameter values and their combination that we define, and the likelihood that we wrote down, what are the kinds of behaviors that we should expect? Sometimes that's going to be crap, right? And then we change the priors, and that's fine, because the priors are not something that we fiddle in order to get a p-value that is below 0.05. But the priors are something that, especially at this stage, are a way to create reasonable expectations, right? If we're predicting height of people, we don't want to set priors that make it quite likely to observe a person that's 1,200 meters tall. And given that we will often have to deal with these nasty link functions, this nasty way of transforming the nice linear space of the linear model into something that is either between 0 or 1 or only positive or what have you, something else, and that creates nonlinear transformations, or that we have relatively, they're not very complex, but relatively complex equations like the reinforcement learning equation, and we have no idea what an inverse temperature is, right? What's an inverse temperature of 10? What is that going to change in the behavior of the participants? I have no idea, right? So we run the simulations. In this case, we run the predictions. And if the behaviors are implausible, we change the prior accordingly, right? Until it makes sense. If we were using informed priors, meaning priors from the literature, right? These would still be necessary because we want to know what the literature would lead us to expect and whether this is correct. Right? So I was playing with some fancy reinforcement learning model that learns several dimensions at once. And if I look at some values from the literature that has been inferred on some empirical data, right, the model expects all my participants to perform all the 9 stages of the experiments. And when I look at the empirical data, half of the participants reach only half of the task. So that means that those informed priors are maybe something problematic, right? And doing these sort of prior predictive checks and seeing how they match with what we would actually know about the task is a way of building critical knowledge. Then we define parameter values for the simulation. Right? So first, we created the inferential models instead. We coded it and everything. Then we say, now we need to feed this model to our simulated data. We go back to our R or Python script that just generated the data. If Peter was here, he would say, Julia, it's the same model. I can tell you publicly on the screen that I was working on a project with him and he couldn't make it work that way. But I know it's a very elegant idea that there are some programming languages where you don't need to shift between R and Stan or Python and Stan, whatever, but here we do. We say, okay, now we try some reasonable simulation. We set the parameter values, we generate the data, and then we fit the model on the data, and we see how it works. Then we assess the model quality, right? We see, given the priors that we have, and we plot the prior, what is the model inferring from the data? And we overlay the posterior. And that gives us some ideas about whether our priors are constraining the inference, meaning our prior is here. For the people of the Zoom, I'm making a narrow prior that goes from whatever, 0 to 3. And our posterior is here, and then making another narrow prior that instead goes from 3 to 6. And this is telling us that our prior is not very compatible with the data. And that if the data were allowed to push our inference
where they point, we would probably have whatever that parameter is, much higher than 6. Right? Because here the prior is sort of keeping it constrained close to 0. That might be a good thing if we are skeptical about these effects. It might be a bad thing, right? Because it might just mean that the prior is not really reflecting likelihood regions. We should have something that's much broader, right? For instance, something that goes from 0 to 10, right? So that the data can allow us to learn about the likely region of the parameter values. But again, we'll see that concretely. We want to do posterior predictive checks. What are posterior predictive checks? They're given that we fitted the model to the data, now we have some posterior distribution of parameter values, and we generate predictions from that model and match them against the real data, which tells us, is the model able to nicely describe the data on which we trained it? Right? Which, it's more commonly than you think, reveals very important issues. I've been working a lot recently on turn taking and the way that turn taking works. In particular, the timing that we take to respond to other people. And all of the papers that I was looking at, they were basically saying, okay, so everything that's below 0 is not good turn taking. You're interrupting something. Let's throw away those data. And then they were saying, okay, then we're gonna fit some sort of Gaussian distribution here, which is gonna tell us what's the average response latency when people are doing good turn taking. And they get some results. For instance, that children, no matter the age, from 0 to 5 years of age, they take about on average a second to respond to their parents. And given that we know that adults take about 56 milliseconds on average to respond, and that I have kids and they don't take 1 second to respond, unless they're playing on some mobile game, that it might actually take longer. That sort of brings some issues, and then you can say, oh, we go and take actual conversation, we simply plot the data, and what we see is something like this. For people of the Zoom, there is a distribution which has a substantial portion below 0, and it has a very long tail on the right, because depending on what we're doing, we might take several seconds to respond. And even if we remove things, right, we have now a truncated distribution that is very high, close to 0, and it has a very long tail, but the predictions of the model are centered much higher, much at a slower tempo than where the peak of the true data is, and their uncertainty, their standard error on the left and on the right, is just meaningless. It's not telling us anything about the data. So if they had done some posterior predictive checks, they would have realized that their model was crap at predicting the data, which is conceptual implication, but it also says that all their inferences are crap. So when we did that, we show that actually it takes about 400 milliseconds for children that are 2 years of age. Yes.
I guess all the steps up until now are like preparing for fitting a good model on some empirical data, right? Or like the actual data, or not simulated data.
Yes.
But I still, and I think I was also doubting it last semester or like how we actually assess when it's good enough.
Yes.
Like all these checks, it seems a bit like arbitrary when we accept it. Like we had whatever model, and there was like one parameter that was like fully recovered, but like whatever, it was okay, and then we went with it.
Yeah.
Does that mean the model is just like we should have used it from the beginning, or like are there principles guiding? Do you know what I mean?
This is, yes. So let's put it like that. There are principles guiding this, but it is a bit like handicraft.
Yeah.
right? So there is a lot of know-how that you develop by doing these models. There is growing research trying to say, can we put some more formal criteria, avoiding dichotomic rules like the p-values or Bayes factor above 3, right? Because different problems have different requisites. And there is no one size fits all kind of answer. What people have been doing is saying, so let's look at a Spearman or an ordinal regression between the parameter values that you reconstructed and the the true parameter values. And I have a master's student, Jesper, who's saying, oh my God, that's crap, because look at this region where the parameter values are very uncertain, but still the average is very much in line with the true parameter values. Shouldn't we notice that this model is really not good at defining with any certainty that region of parameter values? And so and I says, this is a modeling problem. And he's trying to actually build a model that is trying to describe what goes on with different parameters. So you get these secondary parameter values out of the parameter problem. But there is no, yes, this is good, no, this is bad, right? But we'll see examples and we'll try to develop an intuition for when it works, when it doesn't.
Yeah, I have yet to experience like the perfect model. It's always something like, yeah, it's a little bit bad, but it's okay. And like, yeah, I don't know. I hope we will talk more about
Yes.
it.
Yeah, we can actually discuss it because that's what we will do every time we build a model. We will have to evaluate it. So what you can do in an ideal world is that you have a utility function, right? That says, if I make this kind of decision, these are the kind of costs and benefits. And then you can fit the posterior of your model and say, if the mechanism that generates the data that we assume here is the right one, and these are the true parameter values, these is the kind of costs and benefits in the concrete decision scenario. And then it's up to the manager, whoever it is, to sort of say, here is the optimal balance between costs and benefits.
Yeah.
But again, even in that case, there is no one answer, right? There's trade-offs that change. Remember again, I don't want to advocate for doing diagnostic using an algorithm, right? But the example from last lecture, you have false positive of diagnosing a patient, let's say with COVID, and from the cough on the phone, and you have costs of that. Because if you tell them they have COVID, they have to come to the hospital, and that's costly for the system. If you have a lot of false positives, you're gonna overburden the system. On the other hand, if you have too many false negatives, you're gonna have people who are pretty sick, and you're gonna have widespread infection in society, right? So where the optimal trade-off is, it really is a political decision. But we're going to have tools to produce that sort of idea, okay, this is how precise we can get with this model. This is how precise we get with this model. If we have some sort of cost-benefit analysis, we can actually feed the full posterior and get there the distribution of costs and benefits. Good. Once we are reasonably sure that this model is something that we can trust, or in a more realistic scenario, we know the limits of the model, then we can fit it to the data. And then assess model quality and perhaps generalizability, right? Where all the tools that you've learned by doing machine learning, there's no reason that we cannot use them here, right? You fitted a model, you have training data, you have a fit to the training data, but you can also make predictions on how the model would behave, right, for a person that you haven't seen before. And that will give you a testing performance if you want. You can try to overlay the prediction of the model for an unknown person onto 10 new participants that you run, right? We will also deal at a later stage with multi-level modeling, which is not here, and with model comparison and model recovery. Okay, so we create a data set, and here we have done it already, but I'm just putting it here, right? 120 trials. We put a random agent with noise. We loop through a bunch of noise parameter values and bias parameter values. We generate 120 trials for each of these combinations. We plot that to make sure that our simulation is not crap. Right? We always need to verify, right? And now we want to model that in Stan. Let me check a second what the time is. Okay. What is Stan? Stan is not an algorithm, but it's not an acronym. The name comes from Stanislas Ulam, who was one of the people who developed first computers, who was involved in the Los Alamos research on the nuclear bomb. There's actually a pretty entertaining movie called Adventures of Mathematician about the life and biography of Stanislas Ulam. He was one of the people who was involved in the very first Monte Carlo simulation, which was used to calculate the flight and path of neutrons that are needed to ignite atomic bombs. And funnily enough, I was sitting at the swimming pool the other day where my kids swim, and I started talking with this mother of another kid at the thing, and she actually does different kinds of Monte Carlo simulation for different kind of irradiation for cancer at the hospital. And they are all still very much concerned about mapping these neutrons and protons as they irradiate and then hit the body. And they build their own Monte Carlo simulations there, which is pretty cool. So I had something to talk about instead of just awkward. They're good at swimming, right? Yeah. They got so much better than last year. Yeah. It's a bit cold, right? Yes. We could talk about Monte Carlo. Have you tried the Hamiltonian? Are you still using Gibbs? Yes. Okay. It's a probabilistic programming language which is designed to specify probabilistic models. That is, it's not a language that you can use generally to do a lot of programming in general. It's really, you can do more than you would expect, but it's really designed to specify models in terms of distributions of parameters. And the great thing about Stan is that it, instead of using like Box and JAGs, older version of Monte Carlo simulations, it actually implements the state-of-the-art Hamiltonian Monte Carlo simulators, which are really good at most of the tasks you want to do. And we can discuss the samplers a different day because now I want to go more in the details. The way that we integrate R in Stan or Python and Stan, because I know some groups are working in Python, we define the generative model. We simulate the behavior of the model in R or Python, which gives us a data set. And then we define the model in Stan for inference. Then we update our model with the data by using R. If we're using R, ideally, we're using Common Stan R. If Common Stan R doesn't work on your computer, you're going to use R Stan. That's all fine. If you're using Python, there's equivalent PyStan and Common Stan Py to run the Stan model. And then we take the output of Stan and we actually deal with it within R or Python to explore the samples and visualize, etc. When you use Stan, basically what we do, let's say R, we call the Stan program into memory. The Stan program is translated into C++. The C++ program is compiled in architecture-specific machine-readable language, which might take a while. And then the compiled model is run. That is, the model is fit on the data. If you're fitting it on multiple data sets, you don't need to recompile it again. Right? That is, the posterior sample is The posterior space is sample. So if you remember, the way that people used to do Bayes at a certain point was they took Bayes' theorem, right? The probability of the value of a parameter or a combination of parameters given the data is given by the probability of the parameter values in advance times the probability of the data given the combination of parameter values divided a big normalization equation, which was held because it needed to solve integrals. And differentiation is easy, right? There's a bunch of rules that you can apply iteratively, and the computer can do that almost automatically, but integration requires lots of hard work in most cases. But with samplers, we sort of bypass that whole problem because what we do is we don't need the denominator. We don't need the complex equation, which is used to normalize the posterior. What does that mean? It means that once we have the unnormalized posterior, right? We have, okay, let's try, what if learning rate is 0.1785? What's the prior probability of that? Well, we know, we define the prior, we can go and check it. What's the probability of the data that we have given that parameter value? Well, that's easy, right? We can forward run the model with that parameter value 10,000 times, and we can count how many times we produce data that are like the ones that we have in the empirical data set. And then we divide that many times by 10,000, and we have a probability again. We multiply the two probabilities, and when you multiply the two probabilities, suddenly you're not in probability space anymore. That's why we need to bring it, what's the posterior probability in a way that summing the probability of all the possible combination of parameter values, we still get one. Because the word is one, right? And that's where we would go to the denominator. But instead, and in the samplers in general, what we do is we say, nah, right? Let's look around. Now we have this combination of parameter values. We look around at the neighboring combination of parameter values. We see, well, right? Is it more probable if I move one step here? And in Hamiltonian, Monte Carlo, basically we have a momentum, right? According to whether I've been going downhill, more and more probable, or whether I've been going uphill, less and less probable, I might have a momentum. So I'm looking around and I can see that there's a slope this way, right? So my movement as a particle in the Hamiltonian Monte Carlo sampler is going to be deviated by that, but only in a way that is inversely proportional to how fast I was going. So I might be deviating slightly, right? And I keep exploring the space, and I stop here, and I say, what's this region with this combination of parameter values? I write it down, this one sample. Then I do it again, and I move in this space, and I take that combination of parameter values, I write it down, that's a second sample. And then I do that n times, 1,000 times, and then how do I normalize the probability of these parameter values? Well, I can simply count how many there are. I sample the space 1,000 times. If these for a combination happen 200 times, that's a fifth. That's 0.2, right? So I know that the probability of that combination is 0.2, and I don't need to do any integrals. That's what Stan is doing for you. It's simply allowing you to try out the different combinations of parameter values in a very smart way that doesn't take too long and that
doesn't require you to calculate integrals to normalize the probability of these. Right? Does this make sense intuitively? We can get back to that. Yes.
Maybe just one person, I don't expect you to explain the whole thing right now, but I'm just intuitively, what you're explaining here, isn't this messed up by the fact that if you keep sampling, you have, you know, you just said, you know, 0.2 because it was 1 out of 5, but it's a discrete point in a continuous space.
Yes.
So how do you, like, if you took another sample, you are definitely not gonna end up in the same place again, and you would conclude that it's 1/6 and not 1/5.
Well, so the question is, if we want to calculate probabilities in this renormalized space, it goes all nice and dandy from that perspective if the parameter values are discrete, because there's only that many values. But if it's a continuous combination of parameter values, as we always try to do in STAN, what we have is that each combination of parameter values will happen an infinitesimal amount of times. Right? Because there's infinite amount of and I don't have a ready answer for that. But first of all, computers are discrete, so they're not continuous. And second, I think that there's something about kernel smoothing to define the actual distribution, but I'll look it up.
Good. The output samples and diagnostic is made available to R. And now we can very quickly, let me again check the time. No, not really. Well, I'm just gonna very quickly show you something and then we'll take it up again. But when we build a STAN model, this is the structure of the model. And it's a bit different from stuff you built before, even if you build stuff in JAX. Because it requires first to specify which data you're going to feed to the model and the type of the data. That is, if the data is an integer or a continuous variable, if it has specific limits, upper and lower limits. So it's a variable that can only have values between 0 and 1. We specify it there. Why do we do that? Because it saves us time in the long run. We're going to swear a lot when we get errors, but we're going to really tell STAN what it should expect so that if we feed the wrong kind of data, it will tell us immediately. I think it has a specific time in name in Python. It's type something. I can't remember. Anyway, the second is the transform data. So let's imagine that we're feeding all our models simply the choice and the reward, but the model requires the choice of the other person as well, for instance. In the transform data, what we can do is we can operate on the data to create the right variables. And then there's a trick that I'm going to name at a later stage in the course. The third block is parameters, which are the things, the unobserved variable that we want to estimate given the data. We need to define them there. And again, tell STAN which kind of variables they are. For instance, if we're estimating a rate and we want to estimate it on a 0 to 1 scale, we need to tell it that it's a continuous variable between 0 and 1. And we need to name all of them here. Then we have transform parameters. So for instance, if you have stuff like expected value in the reinforcement learning, it's an internal parameter to the model, but it's not really anything that we're trying to infer. It's a deterministic consequence of the learning rate and of the reward and choices, right? You can calculate it. So that's where we do the transform parameters. Sometimes it's also used to simplify other stuff, but we'll get to that at a later stage. And then we have the model block, which is the model where we actually say, what is the likelihood function that generates the outcome given the predictors, right? And also, what are the priors, right? So the model is the priors plus the likelihood. That is the distribution of the parameter values before we even look at the data, and the mathematical form that connects the outcome to the parameters and the data. And then finally, there's the generated quantities, which is a block where we do stuff like predictions of the data given the priors, or the behaviors given the priors, or given the posteriors. It's just a way to generate, after we fitted the model, additional things, because Stan has now been compiled in C++. It's pretty fast. Why not abuse it? And we'll stop there for today.
There's